Hi, welcome to the Quantitative Light Imaging Lab. I'm Mustafa Mir. I'm a PhD student at the lab, and I've been working here for about 5 years now. So as you've already heard in the lecture, at the lab we developed several new kinds of interference microscopes, and the overall method is called quantitative phase imaging. So today I'll talk to you about the newest method to come out of our lab, which is called spatial light interference microscopy. So in order to get to the quantitative phase using spatial light interference microscopy, what we need to do is modulate the phase in the back focal plane of the microscope objective, and just like the phase contrast is doing. So to accomplish that, we use two 4F systems before the image is recorded by the CCD. Now the first 4F system, which is comprised of this first lens and the second lens, all it is doing is adjusting the size of the image, the magnification, so that we can properly fit it onto the aperture of our spatial light modulator. This component over here is a polarizer, and since we want to modulate only the phase of the field and not the amplitude, we have to polarize the light so that it's aligned with the fast axis of our liquid crystal modulator. So after passing through this polarizer, this last lens over here is taking the image, is projecting the back focal plane of the objective onto that final component, which is the liquid crystal phase modulator. So now on the camera, we can see this. We're basically visualizing this the ring that is projected onto the liquid crystal phase modulator, and as you can see, it looks identical to the phase contrast ring, because that is what we're seeing. We're seeing the back focal plane of the objective, which is the frequency domain, which is the Fourier transform of the image. And this is the same thing you would see if you grabbed a regular microscope objective, and if you just peer down one end, you'll see this same phase contrast ring. And so now the goal with SLIM is to modulate the scattered light, which is all around, relative to the unscattered light, which is the DC component, which is lying on this ring. So the way it works in the microscope objective is that there's a thin metal plate that overlays on the unscattered part, which is on this ring, and what that does is it shifts the phase of this unscattered light by pi/2 relative to the scattered light, which is everywhere else, in the middle and around the ring. So I have the SLM running, and I have the camera synchronized with the computer now. So when let me just adjust the focus here. So when I snap an image now, it'll shift the phase between the scattered and unscattered light by pi/2. So this is phase contrast. This is the next pi/2 incrementation, the next pi/2 incrementation, and our third one, and the final back to phase contrast. So from these four intensity maps, now we can uniquely determine the quantitative phase shift through each value in the pixel, which we do using a MATLAB script. And the theory, you have learned about that in lecture already. Since we haven't modified the commercial microscope, we can easily switch between SLIM and a selection of 6 different fluorescence filters. So that way we can not only get the quantitative phase information on the optical, quantify the optical path length differences, which report on cell mass and growth, we can actually say with specificity what the structures we're looking at, and also what we can even use the fluorescence to report on specific cellular behavior, such as what part of the cell cycle the cell is in, or whether it's expressing a specific gene. Okay, so now that you have kind of an idea what the SLIM setup looks like and how we operate the instrument, let me show you a few of the additional components that we have on the scope that have enabled the live cell applications that you have heard about. So one of the basic things that we really benefit from is having a motorized and programmable stage control. So this allows us to scan over large areas, so we can acquire several high-resolution images of small fields of views, and then basically do a mosaic scan and stitch them together to get a large area at the end. And the second component that has really benefited us a lot is having this heating and incubation system. So we have a heating unit and a temperature module and a CO2 module that Carl Zeiss builds, and they build this little incubation chamber that goes over the scope. So we can maintain the temperature inside this chamber at 37°C with the proper humidity at 5% CO2 level. So basically, we can mimic an incubator that's used in a biology lab. So we can keep cells alive in here for we've done up to 2 weeks while imaging the whole time. So that allows us to study the evolution of a culture as it's growing and dividing, or whether we're modulating its behavior in any way. So I hope that after watching this video, you have a better idea of what the actual physical SLIM system looks like, and what is actually required in terms of space and optical components to build a SLIM system of your own. And you've heard in lecture of the theory behind the system and the various applications. So thank you for coming to visit our lab. And if you have any questions, please feel free to contact us or visit our website. Thank you.